Okay, so if you're watching this, it means that I am at jury duty and have never been more proud to be an American citizen. The paper that I'm going to discuss is preparation and detection of a mechanical resonator near the ground state of motion. And basically what this group, it's a group from Caltech, what they're trying to do is see if they can get a macroscopic object, a resonator, a mechanical resonator, just like the other two presenters discussed, into its energetic ground state. In other words, its ground state of motion. And the thought is that if they do this, they can observe quantum effects in this object, which would be something pretty interesting. You see quantum effects in things that have very, very little mass, like atoms and photons, and even things as large as fullerenes. But something on the scale of like a nanomechanical device, this would be something different. So, for a little background, recall for a quantum harmonic oscillator, the energy level is given by this expression, where n is the quantum number, h bar is Planck's constant divided by 2 pi, and omega is the resonant frequency. So if you're at the ground state, n is going to be 0, and this is the expression for your ground state energy. So if you want to reach the ground state, you want to make getting there easier, you need E sub 0 to be as large as possible, which means you need to have a large frequency. Now, frequency is, of course, given by square root of k over m. K is the spring constant of the resonator, m is its mass. So you want a small, stiff resonator, but you don't want it so small and stiff that you can't measure its amplitude. So it's a bit of a balancing act. So what this group did is they created this mechanical resonator made of niobium, aluminum, and silicon nitride, with the dimensions shown, and those are substantial dimensions. 30 microns in length is something easily seen under microscope. And they created this thing, the beam here. That's the niobium beam. It's 75 nanometers away from this gate that they also fabricated, and we'll talk about the purpose of that in a moment. And this thing acts as a freely suspended resonator that's doubly clamped at both ends, and it has a resonant frequency of 2 pi times 6.8 megahertz, and a quality factor of a whopping 10 to the 6 when you get down to 100 millikelvin. And yes, you need to get down at least that far to see anything approaching a quantum effect. So again, here's the resonator, and here's the system that it resides in. This is their whole experimental setup. So here's the resonator. It's along with the gate. It's going to be inside this large apparatus, and it's going to be thermally isolated. And we're going to do that by, first we reduce the temperature with some liquid nitrogen, then we reduce it further with a couple of different isotopes of liquid helium. We have these things called black body attenuators, which are basically filters to remove any sort of stray or ambient electromagnetic energy other than the little bit that we want to get through, and we'll talk about that in a second. And then in this chamber here is really the thing that we're trying to measure. And using this setup and a few other methods that I'll talk about in a moment, they got temperature as low as 20 millikelvin. And then this section here, this chamber, is what I'm going to talk about next. This is where everything happens. So inside here, there's a resonating cavity. That's this SMR, the superconducting microwave resonator. It's this resonating cavity with a niobium superconducting film. And inside the cavity, electricity and magnetic fields are resonating, and they're pumped by this microwave source over here. And the resonator behaves and is shown as if it were an LC circuit, and it has a resonant frequency of just a little bit more than what the nanoresonator has. It's 7.5 megahertz times 2 pi. And so coupled to the SMR then is the nanomechanical resonator, and it's capacitively coupled. So when the mechanical resonator oscillates, it changes the capacitance here with this gate that we saw earlier. So in a really naively way of saying it is, if you had a parallel plate capacitor, the capacitance is given by epsilon A area over D, the distance between the two plates. So as this thing resonates, it's essentially changing the distance between, and therefore changing the capacitance. That's not exactly the right model, but it gets you there as far as getting the concept. So changing the capacitance alters the overall capacitance of this whole circuit here, and therefore modulates the frequency of the LC circuit. So the mechanical resonator at the same time also feels a force from the potential across that capacitor. And there's a phase lag in the force relative to the resonator motion because the LC circuit, there's a lag in the response time of the LC circuit with respect to the mechanical resonator's motion. And all of these things are happening with respect to this microwave source frequency, and we're going to call it omega sub p. It's a pumping frequency, and that frequency is fixed. And it turns out if you use a pumping frequency that's less than the frequency of the LC circuit, it produces, the phase lag produces a force that opposes the resonator motion, which in turn dampens the motion. And if that damping is done correctly, then it effectively cools the resonator. And that's how you get this thing down to extremely low temperatures. And specifically when the pumping frequency is the difference between the superconductor resonator frequency and the mechanical resonator, it's essentially, it's cooled by the equivalent of one pumping frequency worth of quantum energy. So this cooling process is called an up conversion. You're extracting the phononic energy, the lattice vibrational quanta, from the mechanical resonator. And essentially you'll know that you reach ground state when you can't extract any more phonons out of this thing. There are 0 phonons. And the state of the mechanical resonator is going to be reported in terms of this thing called the occupation factor. And that's essentially just the expectation value of the resonator quantum number. And they express this term called the deep quantum limit. This is what they're after. If they can get this expectation value to be way less than 1, but essentially 0, then they'll know that they're at the ground state. And they did pretty well. This is actually quite a bit better than most other studies to date. So they got this expectation value down to 3.8 plus or minus 1.3. And so that is this line here, the blue, closed blue circles here. So very close. The main limitations is the superconducting resonator just had fluctuations which increased temperature. And but the main thing was that as you increase the pumping power, you can extract more energy out of the resonator, out of the mechanical resonator, but only to a point. So this is the pumping power down here, and it's expressed in terms of the quantum number of the pump itself. But at some point, increasing the pumping power also means that you'll induce a current in the metal of the resonator itself, which, due to scattering of the electrons in the metal, you have ohmic resistance that pushes heat out into the helium bath, and as a result, the best they could do is really kind of keep a steady temperature of about 146 millikelvin, which turns out to be not cold enough. So what do you use something like this for? Well, parlor tricks, TED Talks, they exist. The main thing is they think that they can potentially use this thing for quantum computing of some variety. And the idea is each quantum state is a qubit, a quantum bit. And you could do things like couple several mechanical resonators together, two of them together, and it would essentially operate as a quantum AND, or a quantum OR gate. This is way, way, way off into the future. As of this paper, they weren't able to achieve anything like this that would suggest that this was just over the horizon. But as it turns out, here's a little epilogue. So here is this paper that we were just discussing, and this came out. It was published at the end of December 2009. And then this paper later came out stating that they had reached the ground state. So they had a single phonon control of mechanical resonator. And this is a pretty interesting paper as well. And it came out only 4 months later. So I guess, and this is from a group from just up the road, UC Santa Barbara. So, and it got the Science Breakthrough of the Year moniker. So I guess the group from Caltech was maybe a little sad about this, but it was pretty interesting. This is a good paper to take a look at. And actually, there is a TED Talk by the lead author, this O'Connell guy, that you can take a look at. It's kind of interesting. That is it. Here are some references. And thank you very much for your time.